Hi, today I'd like to share how to compress recurrent neural networks using hierarchical Tucker tensor decomposition. RNNs have been widely used in sequence analysis and modeling. However, when processing high-dimensional data, RNNs typically require huge model sizes, thereby bringing a series of deployment challenges. To overcome these limitations, we propose to develop compact RNN models using hierarchical Tucker decomposition. HT decomposition brings a strong hierarchical structure to the decomposed RNN models, which is very useful and important for enhancing the representation capability. From this architecture, compared with vanilla LSTM, the proposed HT-LSTM decomposes the input to hidden layer to HT format, while keeps the hidden to hidden layer the same with vanilla LSTM. Why the proposed HT-RNN is better than the others? The first reason is parameter sharing. The decomposed parameters in the same level can perform parameter sharing via transfer tensors. The second reason is stronger representation power. The hierarchical structure imposed on the input to hidden layers makes RNNs can exploit and extract the important representation and pattern from high-dimensional data in a much more hierarchical way, thereby significantly improving RNN models' representation capability. The third one is lower storage and computational cost. HT decomposition inherently provides higher complexity reduction on the same size tensor data with the same selected rank. Here is an illustration of HT decomposition with D equals 4. All the dashed lines and boxes describe a binary tree with root D equals 1, 2, 3. Here X is decomposed to a set of orange-colored transfer tensors and blue-colored leaf frames, which are the only tensors needs to be stored. Here is the forward computation direction in the HT layer. First, the input vector X is tensorized to a tensor X with 4 dimensions, and then tensor contractions are performed via the arrow directions. Finally, the output tensor Y with also 4 dimensions are obtained, and the output vector Y is what obtained by reshaping. To better understand the impact of HT decomposition on RNNs, we analyze the theoretical complexity of HT-RNN and compare it with the vanilla uncompressed RNN, as well as other tensor decomposition-based RNN models. This table summarizes the space complexity and time complexity of different RNN models. It is seen that compared with the other compressed RNN models using tensor decomposition, HT-RNN has the lowest space complexity to store the model parameters. Besides theoretical complexity analysis, we also verify the low-cost benefits of HT-based compression via empirical experiments. Figure A shows the number of parameters to store a compressed weight matrix, and Figure B shows the number of needed operations for multiplication between the compressed weight matrix and vector. It is seen that HT-based approach indeed achieves lower costs, especially on storage requirement. We evaluate the performance of HT-based RNN on different datasets, which are categorized to end-to-end training and training with pretrained CNN. In the first category, end-to-end training, on both UCF11 and YouTube Celebrity dataset, the proposed HT-LSTM outperforms the state-of-the-art including TT, BT, TR, and the vanilla LSTM. In the second category, the proposed HT-LSTM also outperforms the state-of-the-art TR and the vanilla LSTM. In this work, a new RNN compression approach using hierarchical Tucker decomposition is proposed. The HT-based RNN models exhibit strong hierarchical structure as well as low storage and computational costs. Experiments on different datasets show that the proposed HT-LSTM model significantly outperforms the state-of-the-art compressed RNN models in terms of both compression ratio and test accuracy.